Okay, let's talk about independent events. Uh, by definition, uh, independence means statistical independence. 통계적 독립성 in Korean. Abbreviation, you may say SI. Uh, we have two events here, A and B. Uh, Always there should be some kind of overlapping elements between A event and B event. Let's say we have two elements overlapping. For example, event A may be uh, the tall students, and event B may be the male student. Okay. For two events A and B, let's say PA, the probability of A, and PB, the probability of B, is greater than zero. Greater than zero means uh, the event occurs. If PA is not affected by the other events B or vice versa, then that is to say conditional probability A given B is the same as just probability of A. That means the sample space is not reduced, okay? And this event B does not have effect on the event A. And also, probability B given A, the conditional probability B bar A, given A, is the same as probability B, then uh, the intersection probability of intersection event A uh, cap B is the same as uh, the multiplication of each probability PA and PB. So uh, because the probability A given B or probability B given A here does not this conditional event does not have effect on the other events. So therefore, probability A intersection B is the same as multiplication of both uh, event probability of those events PA and PB. So uh, uh, it is actually the numerical thing. For example, we have a sample space S here, and uh, A has four elements, so with the same probabilities. B has also four elements, and overlapping region we have two elements with the same probability, and the outside of A union B we have two elements in this universal set S or sample space S. Then we have even if we have the same probability numerically, uh, A and B are independent events. Why? Because PA intersection B, if you take a look at PA intersection B, is uh, here only two elements among 8 elements, so it will be 2 over 8. Okay, let's take a look at PA. PA is uh, we have four elements, so it's 4 over 8. So is 1 over 2. PB is the same because we have 4 elements also with the same probability, and each probability of each element is the same. We have say 4/8. Okay. So if you multiply probability A and probability B, you get 1/4. So it's the same as probability A multiplied by probability B, 1/4. Okay, but you have to be very careful. Note that we were talking about a mutually exclusive event, but this mutually exclusive event is not the case. We are talking about independent events. Why? Because the intersection of A and B is the empty set. Because of this, probability is 0. This means PA multiplied by PB is 0 for mutually exclusive event to be independent, which is not possible because by assumption, probability A should be greater than 0 and probability B should be greater than 0. The both conditions should be held. So, therefore, it cannot be both mutually exclusive and statistically independent. They are not uh, comparable with each other, competitive with each other. So if you generalize for A1 up to AN events, then intersection of probability of that intersection of n event A subscript I is just multiplication of each probability of the event AI. Now we can talk about Bernoulli trials, Bernoulli 시행 in Korean. By definition, the Bernoulli trials is repeated independent experiments. For example, flipping a coin, pass-fail in an exam, hit-miss a target, win-lose a game, receiving 0 or 1 in a bitstream, and successful failure, etc. In this case, the previous event and also you have probability, and this previous event does not have influence upon the next event. Okay, passing an exam, this event, failing an exam, let's say this is another event. Both does not have influence upon each other. Okay, let A be an elementary event of repeated independent trials. For example, flipping a coin. Then P of A, probability of A, is equal to P, which is the probability of a success. If this when you flipping a coin, if this coin is a fair one, then this theoretically the probability of success or probability of a head appearing will be 1/2, 0.5. But in practical sense, this is not always true, because as you try 1,000 times, and it's 1,000 times, for example, then the probability of head appearing is not exactly 500. It's maybe 498 or 501. And probability A complement is 1 minus P, which is Q. This is the probability of a failure. So as you repeat trials, the number of repeated trials is n, and the number of successes is k. Then the number of instances 경우의 수 is equal to binomial coefficient. It becomes binomial coefficient or Bernoulli binomial coefficient, which is combination uh, among n you choose k, which is defined as n factorial over k factorial n minus k factorial. So um, if you have the probability of the event A, which occurs exactly k times, for example, you have number of successes k, or uh, number of 1 data coming in, or when you're flipping a coin, the head appears k times, then this probability is equal to combination n, you choose k, p to the k multiplied by 1 minus p to the n minus k. Because you have the number of instances combination n k, and each probability is independent, so you multiply each probability. So it's going to be pk, which is which stands for the success probability of success k times, multiplied by 1 minus p to the n minus k, which is the probability of failure n minus k times. Okay, now we take a look at examples. Example number 1. We have a box, and inside the box we have 100 registers. And if you take a look at the right hand side, you have resistance, three kinds of resistance: 22 ohms, 47 ohm, and 100 ohm. Each register has some kind of stripes, and the last stripes, the color of the last stripe stands for the tolerance. This is error within 5% or error within 10%. If it is silver, then it will be 5%. If it is gold, then it will be 10% tolerance. So inside this box, you put 100 registers inside. Among 100, we have 22 ohms, 24 of them, and 47 ohms registers, and 32 100 ohm registers. So event A is, let's say we have the event drawing a 47 ohm register. When you pick up a register in a box, blindfolding, for example, you don't look at inside the box. Event B is drawing a register with 5% tolerance. Event C is to draw 100 ohm register. So take a look at the first one. Find probabilities PA, PB, and PC. PA is you pick up 47 ohm registers inside the box. So it's going to be, you have 44 of them, 5% and 10% together. 44 of 47 ohm registers inside the box. So it's going to be 44 over 100, 0.44. PB is, let's say this is the event drawing 5% tolerance registers. Then it's going to be 5% is, we have inside we have a 10 over 22 ohm, 28 over 47 ohm, 24 over 100 ohm registers. So you add it together, it will be 62 5% tolerance registers. And the probability C is picking up 100 ohm. So for both 5% and 10%, you have 24 and 8. You add it together, it will be 32. You already know 32 registers of 100 ohm. So PC will be 32 over 100, 0.32. Okay, the question number 2. Uh, Find all joint probabilities PA intersection B, PA intersection C, and PB intersection C. PA intersection C, B means uh, A is 47 ohm, and at the same time, event B, which is 5% tolerance. So inside the box of the table, in the table, you have 5% and uh, 47 ohm, so it's going to be 28 of them among 100. So therefore, it's going to be 0.28. Probability P, A intersection C, you have 47 ohm at the same time 100 ohm. By the way, this is an impossible event. So this is the empty set, which is 0. The probability of A intersection C should be 0. Now, the probability B intersection C, take a look at this. Uh, Event B is 5% register, and event C is picking up 100 ohm. So 5% at the same time, 100, we have 24 of them. So the probability of B intersection C is 0.24. Question number 3. Find conditional probabilities PA given B, PA given C, and PB given C. You have other choices, but let's take a look at only 3 cases uh, for simplicity. Probability A given B means uh, uh, by formula, probability A intersection B divided by probability B. So you have already computed probability A intersection B in the question number 2, 0.28. So 0.28 divided by probability B, which is already computed in question number 1, 0.62. So it's going to be 28 over 62. And probability A given C. What is the condition C, which is picking up 100 ohm resistor? But this is A is drawing a 47 ohm resistor, which is an impossible event. So it is 0 automatically, because intersection A, intersection C is the empty set. And probability B given C, which is probability B intersection C over probability C. Probability B intersection C is already we have computed in the question number 2, which is 0.24, and probability C is already computed also in the question number 1, 0.32. So it's going to be 24 over 32. Okay, for the second example, this is an elementary binary communication system which transmit or receive 0 or 1 signals from the channel as a kind of communication system. Let's define event of sending symbols and receiving symbols. Okay, B1 is the event, the symbol before the channel is 1. We have a channel which is communication transmission or communication line or some kind of media cable, or you can think of this as maybe aerial transmission. B1 is the event, the symbol before the channel is 1. So we are sending 1 signal or symbol. B0 is the event, the symbol before the channel is 0, that means we are sending 0 signals uh, as an input. A1 is the event. The symbol after the channel is 1. So that means we are receiving one signal or one symbol at the receiving side. A0 is the event. The event after the channel is 0. So we are receiving 0 signal at point A. The reason for this input-output symbol B and A respectively is that we are trying to find a conditional event, for example, as a B, and then trying to find the inverse probability from that conditional probability. Now we assume that binary symmetric channel. Okay, so that means we are sending binary signals 0 and 1. The selection probability of 0 or 1 for transmission, we assume that for this binary communication system, probability of B1, that means this, we are sending one signal as an input is 0.6, and we are sending 0 signals is 0.4. The probability is 0.4. So this is some kind of a priori probability. And reception probability given A1 was transmitted. This is a conditional event, and the probability of a conditional event A1 given B1, meaning we know that at the transmitter side we are sending one signal, but at the receiving side the probability of receiving 1, which is correct, is 0.9. So this is okay. You can think of this as a success. And also we have a probability A0 given B1 is 0.1, which is kind of error because we are sending 1 but receiving 0 at the point A. So the probability of A0 given B1 is 0.1, means we have a 10% error. Even though we are sending one signal at the transmitter side, we are receiving 0, that means we have an error. Okay, reception probability given 0 was transmitted is PA1 given B0. So we are sending 0 signal at the B side, input side, but we receive one signal at the receiving side. So this is kind of error. So probability A1 given B0 is 0.1, 10% error. And probability A0 given V0. So that means the reception probability given 0 was transmitted. So probability A0 given B0 is 0.9. We don't have any error because we are sending 0 signal, and we know that. And then the probability of receiving 0 is 0.9, 90%. So this is correct. So if you take a look at the number, this is symmetrical because the probability of error and probability of success is the same respectively. So you can think of that probability, whether or not we are sending 0 or 1, receiving probability. If we are sending 0, receiving probability of A1, probability A1 given B0 plus probability A0 given B0 is always 1, because A1 and A0 are mutually exclusive event. We cannot simultaneously receive 0 and 1 altogether. It is impossible event. So those conditional event uh, is mutually exclusive. So here, this is the transmission uh, of uh, binary symmetric channel. So we have a box over there which specify the conditional probability for the channel sending one but receiving one or receiving zero. By the way, here we have a notation 2 means zero. We are sending receiving zero. A2 is receiving zero, event of receiving zero. B2 is sending zero at the transmitter side. So I changed the symbol to the number 2 to 0 number because it coincides with the 0, 1 symbols. Okay, so continuing the example for this elementary binary communication system with the same symmetric channel, the received symbol probability, that means in Korean 측정된 출력 확률은 총 확률로 구한다 하는 거죠. Okay, so probability A1, which is the total probability, equals to, as you know the formula, we have a conditional event, two of them, B0 and B1. So PA1, we are sending one, we are receiving one at the receiver side. So PA1 equals to PA1 given B1 multiplied by PB1 plus PA1 given B0 PB0, which is we know already the a priori probability is 0.6 for PB1 and PB0 is 0.4. And also conditional probabilities are 0.9 and 0.1 for PA1 given B1 and the PA1 given B0 respectively. So if you compute this, you get 0.58, which is similar to 0.6, but it's not exactly 0.6, which is a priori probability. This is a little bit different. Okay, PA0, another total probability receiving 0 at the receiver side, which is from the formula PA0 given B1, PB1 plus PA0 given B0, PB0. So the a priori probability is 0.6 and 0.4 for PB1 and PB0 respectively. And also the conditional probability is PA0 given B1 and PA0 given B0 is 0.1, which is kind of error, and 0.9, which is okay, respectively. So it's if you compute this, it will be 0.42. So you add together this total probability, it will be 1. So the received symbol probabilities are computed from the formula of total probability if you have this conditional events. So PA0 receiving 0 symbols at the receiver side, and the PA1 receiving 1 signal or 1 symbol from the receiver side is 0.42 and 0.58 respectively. Now we will find the inverse probability, which is from the base formula. This is 결과로 나타나는 사후 확률은 역확률로 구한다 in Korean. So we change the conditional event because this means we already know the fact that we received one symbol or zero symbol at the receiver side. But what is the probability of sending 0 or 1 from the transmitter side? This is a little bit different concept, which is called a posteriori probability, which is called 사후 확률 또는 후험적 확률 in Korean. So PBK given AK, K may be 0 or 1, is called a posteriori probability, 사후 확률. Remember that PBK is a priori probability, which is 사전 확률, 선험적 확률 in Korean. So if you compute this inverse probability, we have a total 4 instances, because at the transmitter side we are sending 0 or 1. At the receiver side you are receiving 0 or 1. So combining those instances, you will get total of 4 of them, 4 cases. So probability B1 given A1, which is equal to, from the formula of base formula, PA1 given B1 multiplied by PB1 divided by the total probability PA1, which if you compute this, it will be 0.931. So it will be correct transmission of the symbol information. And PB0 given A0, which is equal to PA0 given B0 multiplied by PB0 over the total probability of receiving 0 signal, so PA0. If you compute this, it will be 0.857. So yes, you already know the fact. At the receiver side you get 0 symbol, but what is the probability of sending 0 at the transmitter side? That's called a posteriori probability, and this is correct one also. What is PB1 given A0, which is a kind of error? You know you received 0, but what is the probability of sending 1? So that's a little bit different concept of error occurring in those events. So which is PA0 given B1, PB1 over PA0, which is 0.143, kind of error. And finally, PB0 given A1, which is PA1 given B0, PB0 over PA1, which is 0.069. This is error because you know the fact that you get the symbol 1, but what is the probability of sending 0 at the transmitter side? It's kind of error also.